So we're going to start the second half of this session, moving from the general overview of gas in protoplanetary disks, dust in protoplanetary disks, and now move on to a very specific aspect. And Colette Salyk, is going to tell us about volatiles in protoplanetary disks. Please, Colette.
Okay, sounds like that's on. So I'm very excited to be here today to represent my illustrious team here and talk to you about volatiles in protoplanetary disks. So to make sure we're all on the same page, let me just remind you what a volatile is. This is something with relatively low sublimation temperature. And for the purposes of our chapter, we're defining this as something like sublimation temperatures below a few hundred Kelvin. So you'll see that this includes things that are essentially always in the vapor phase in the disk, but also things that transition between the vapor and the solid phase, or what we might think of as ices. And I don't have the chance to cover everything in our chapter today, obviously, but what I want to focus on is the connection between disk volatiles and planetary properties. So let's think about the solar system for a minute. And we know that in the outer disk, we have volatile-rich planets, while in the inner solar system, we have volatile-poor planets. And the reason we think this happens is that in the inner solar system, in the disk phase, the volatiles are in the gas phase. And so they don't get incorporated into the bodies. But in the outer disk, the volatiles can be in the solid phase, and so they do get incorporated into planets. So this is kind of a qualitative feeling for what happens in the solar system. So let's look at some actual data. So this shows the chondritic abundances for various elements compared to solar abundances. And what you can see immediately is that some of the elements that tend to be in the gas phase do not show up even in chondrites. And something very dramatic happens, in fact, if you just move a few AU to the Earth's distance. So now I'm comparing Earth abundances with solar abundances. And what you see is now your noble gases are not even on the plot anymore. And you see quite refractory elements now being depleted from the Earth. But what you might not have thought about if you're familiar with this picture is that what's important is that you need to know what is the actual carrier of the elements to know whether they're going to be in the gas or the solid phase. So there's no such thing as just atomic carbon throughout the disk. Instead, you have to ask, is the carbon CO, or is it perhaps graphite? And as you can imagine, those would have very different properties in the disk. And you can play this game for whatever atom you'd like. Nitrogen, for example, is it in N2 or is it in organics? This would have a very different effect, as these have very different volatilities. So the solar system provides a fossil record of these processes, but now we can actually ask, and this is the power of studying protoplanetary disks, what is the volatile content of the actual disks out of which the planets formed? And can we measure where the volatile species are and where they're in the solid and vapor phases? Now, this type of chapter did not appear in PP5, and the reason is that a lot of the pioneering work has happened in the last 5 years, and this is really exciting work. So a lot of the pioneering work was done with the Spitzer infrared spectrograph, IRS, and really with techniques pioneered by John Carr and Joe Najita, and this shows their discovery image, or spectrum, if you will, showing some of the molecules that were observed in this one disk, AA tau. And what I'd like to make sure to point out here is that here is the model below, and all of these features that you're seeing are actually due to water vapor. So this is not, this is a very exquisite high signal-to-noise spectrum, in other words, and it's just littered with molecular features. So it's one thing to just detect molecules in a disk, but what I think is even more exciting is that it's turned out that these features are very common. So that means you can actually use these features to study the bulk of disks that we know about. And this just shows a histogram of some of the molecules that have been observed in low-mass stars. And you can see that all the molecule detection rates hover somewhere in the 40–50% range. And I would add that I think the data suggests that as we increase the sensitivity of our instruments, those rates are going to go up even higher. Now, Herschel has also played a role in this revolution of being able to study volatiles in disks. And in particular, it's been used to study water. And we're going to hear a lot more about this from Ted Bergen in his talk. But I just want to say that the Herschel observations, when the water vapor in these observations generally comes from further out in the disk, and in fact, probably where the water is already frozen out. So it gives you leverage to study the full disk and actually study the water where it's primarily in the vapor phase and where it's primarily in the solid phase. And we heard a lot about how chemistry is being used, especially to study physics, using millimeter data from Dmitry Semenov. And he also pointed out, however, that the number of disks where we've been able to study chemistry with millimeter arrays, I think his number was 12. So this is a very small number of disks, and in addition, it's probably biased because it is, unfortunately, currently just the most massive disks. However, that's going to change in the very near future, and so I predict that PP7 will have a lot of information about volatiles as studied with ALMA. Now, it's important to realize that when you want to study chemistry of disks, it's really important to use a variety of facilities that cover a range of wavelengths. And this is a nice illustration of that from Simon Bruderer et al. So this shows the contribution for a given line in the disk. So you're looking up from above, and what you see is that if you look, for example, at CO 30 to 29, you're probing mostly the disk in the tens of AU region. On the other hand, if you look at a low-lying transition, 3 to 2, for example, you're now probing much further out in the disk. And it's the combined observations of all of these transitions that gives us a complete picture of a disk. Dmitry alluded to this as well, which is that emission lines give us extra information that you can't get just from an image. And this can be very powerful. So one thing you can do is just look at the emission temperatures of your lines and determine where the lines are. Another thing you can do is if you actually have resolved emission lines, you look at the Doppler shift of the gas, and then you use Kepler's law to actually locate the gas in the disk. And one interesting thing about this point is that the regions very close to the star and the disk have very high velocities. So you actually have sort of a bias towards being able to resolve structure that's on very small scales in disks. So you can probe potentially very small radii. Another thing you can do is study deviations from the expected Keplerian motion. And that includes turbulence, which we've heard a little bit about. And I'm going to highlight a little something about eccentric orbits here. So it turns out that if you have a planet in a disk, the orbit of the gas that is just outside of that planet can become eccentric. And if you observe gas lines from that eccentric gas, it can be eccentric. The line shape can reflect the eccentricity. And there's been an actual observation of this effect from Laskowski et al. And we're going to hopefully hear more about the effects of planets and disks from James Muzzerall. OK, so back to chemistry. One way to think about the chemistry in disks is to ask, what is the path of the volatiles? And there are sort of two end-member ideas for what happens with the chemistry. One I'm going to call inheritance. And the idea here is that you have a cloud, and you have your chemistry in the cloud, and it comes in, and it doesn't get processed, and that determines your chemistry in your disk. Another end-member possibility is some sort of complete reset of the chemistry, and so you lose the history of what came before. And both of these ideas actually have a lot of history in the solar system or cosmochemistry community. So I just want to talk a little bit about that. One piece of evidence for inheritance comes from comets. So this actually shows that if you look at cloud abundances of various ices, these actually resemble cometary abundances. And then there's a whole other story that has to do with D to H ratios, and I'm going to leave that to Ted Bergen. There's also a lot of evidence for the idea of reset in the solar system, and this is really the basis of the condensation sequence that we're all taught about. So the idea here is that you need to heat stuff in the disk to such high temperatures that you actually melt or vaporize very refractory materials like CAIs and chondrules. Another thing you can do is look at the compositions of the bodies in the solar system. And it turns out that if you're to take, for example, a body that has the same composition as the sun or the ISM, and you try to make an Earth out of it, you cannot do that. So the compositions don't match. So this is, again, evidence that the chemistry has changed. And there's a very interesting result showing that, in fact, this phenomenon might be more universal than just the solar system. So this shows that if you look at polluted white dwarfs, so these are white dwarf stars that show evidence for excess materials in their photospheres, they actually also show a depletion of carbon relative to iron, for example, shown here. So, and here are all the white dwarfs sitting, in fact, even more depleted than the Earth. Now, what about in disks? What can we say about these phenomena in disks? So one of the pieces of evidence, I think, for a reset phenomenon in disks is one of the themes that we're hearing a lot about at this conference, which is that disks undergo very energetic events. And we heard a little bit about this from Amy Stutz, and we're going to hear a lot more about this from Joel Green, but I want to just mention one thing that I think helps us understand this picture. And that is that if you look at the spectra of Fu Orionis stars, so these are stars undergoing extreme accretion events, what they actually look like is stellar photospheres. So this is an M-giant photosphere. So that immediately tells you that you don't have a quiescent disk that is primarily heated from above anymore. Now you have something that looks like a star, so it's heated from inside. And it's heated to quite high temperatures according to models. So this seems to be evidence that disks undergo very energetic events. And now we actually have observations of the chemistry in inner disks, so we can ask the question, does that chemistry resemble the ISM chemistry or the cloud chemistry? And what you can see here, so this is the disk chemistry and the cloud chemistry, that they don't match. So there seems to be already some clear evidence of a reset of the chemistry, at least in the inner disks. But are there parts of the disk where the chemistry really is inherited? Well, I would say that we don't know yet from observations, but models do predict a significant inherited component. In fact, we heard a little bit about this already from Ruud Visser this morning, and his models followed parcels of material from the cloud to the disk and asked how much were they processed. And the takeaway from this plot is that this entire region of the disk here shown in white is a region of the disk where water ice comes into the disk and never even evaporates, so it's completely unprocessed. So the models seem to suggest that we need to have an inheritance component to the disk that may be significant. And this is something that I think we'll be seeing some investigation of with ALMA. OK, so the condensation of volatiles does affect the compositions of planets, but it can have an even more dramatic effect. And we all know that in the solar system, there's quite a dramatic difference in the planets at Mars's distance and here at Jupiter's distance. And we suspect that this has to do with the snow line, which we think is somewhere in between those two. So you not only get a more volatile-rich planet, but a completely different type of planet now, a giant planet. And one of the possible reasons for this is that at any condensation front, the freeze-out of the volatiles very much increases the solid surface density. So this is an example of, this is just a pie chart showing the cloud ice abundances, just to give us a sense. And so if you look at, for example, the mass of the silicates, it's comparable to the mass of water ice. And so already you can close to double your solid content if you are over the snow line. And then if you pass the CO snow line, you get even more ice. And this may have very dramatic effects on the formation of planets. So this is just one model demonstrating one of those possible effects from Pollack et al. And it shows that two paths for planets, one is this and one is that, and how their growth is affected by having two different solid surface densities. And in fact, the solid surface density here is only half of that value. And in one case, you end up with a very massive planet, and while this one kind of stalls out. Now, for very large ice lines like CO, there's actually the possibility of directly imaging the condensation front, or the freeze-out. And I wish these were real images, but they're not yet. But these are models of different tracers of the CO freeze-out line. It turns out that CO is a little bit difficult to directly image the CO snow line, but you can use tracers. So these are 3 different chemical tracers and predicted ALMA images from Charlie Chi et al. These are actual data of some ice lines. As you can see, these are from the SMA, and so you can see the hints of this kind of structure. But as you can see, we have a ways to go. And I can promise you that ALMA is going to come to the rescue very soon. Now, for water, it's a little bit more difficult. You can't really directly image the water ice line. So we have to use some slightly different techniques here. And what we do instead is look at the relative amounts of water vapor at different excitations. And this depends on the distribution of water vapor in the disk. So here's an example of if you have a water vapor abundance profile that looks like this, and of course if it suddenly drops off, that's your snow line right there, then if you move that snow line around, you get dramatically different water vapor spectra. And you can also see that you can also play with other parts of that distribution. So you can change the outer disk abundance, for example, or the inner disk abundance. And you'll also notice that they're not degenerate. So you can actually have some hope of really deriving the water vapor abundance profile. Now, the first attempts to do this came from Meyerink et al. 2009. And what you'll see here is they're comparing Spitzer IRS spectra here with models where they've tried different values of the snow line. And this, for example, has a 1 AU snow line. This has a 5 AU snow line. And what they say is that because these very strong lines here don't appear very strong in these spectra, the data are slightly more consistent with a 1 AU snow line. I think that there's still a little bit of work to be done to be very secure about this result. But in any case, it's the first attempt. So what do we actually expect about the snow line? Where is it? Well, I think a lot of us, even though deep down we know this isn't right, we still think about the snow line as a line. And we think about it as the classical value of somewhere around, this is 2.7 AU from Hayashi et al., but something around a few AU, obviously between Mars and Jupiter. And we think it doesn't evolve. But the reality is probably a lot more complicated than that. So this shows some possible models for the evolution of a snow line. And you'll see, first of all, it matters what your star is like, because that provides the heating, but also even an individual star, because its luminosity evolves with time, that snow line evolves with time. And you can imagine other things. It would depend, for example, on how the heating is distributed in the disk. So there's a lot of unknowns. One thing that hasn't also been discussed very much is that at the very late stages of the disk evolution, we know that the disk clears. So we're going to hear about this from Ilaria Pascucci and from James Muzzerall. But if the disk clears, then all of a sudden, your disk sees a lot more radiation, so the snow line moves out again. So we can now place our first measurement of the snow line on this kind of plot. And I should point out that what we saw was a surface snow line. And so you can think of that as an upper limit on the mid-plane snow line. But roughly speaking, it's somewhere in the ballpark of where we'd expect it to be. Perhaps if you're talking about a one solar mass star, maybe it's a little small. But I think we're in the very early stages of really investigating this. Now, there's been a second attempt to measure a snow line, and this was done, I would say, very carefully. And I'll just show you a few of the plots from this work. So this shows the abundance profile of the water vapor in the disk, and just one of the parameters that were varied. This is work by Coco Zhang et al. And you can see that moving the snow line out, this is where the water vapor drops off, has a dramatic effect on some of the emission lines, in particular things in the mid-infrared. And it's interesting to note that if you look at the mid-infrared, or shorter wavelengths in the mid-infrared, or out in the far infrared, the data are actually less sensitive to the snow line, but these lines end up becoming sensitive to other parts of the water vapor profile. So you can actually really have a hope of deriving a full abundance profile for water vapor. So what is the result? Well, in this case, it's a transition disk, and it has an inner cleared region, and the water vapor sits just outside that cleared region, and then the snow line is just outside of that. So it's just a narrow ring of water vapor. So we can place this on our plot as well. Excuse me. And what you can see is this actual evolution as the snow line increases because the disk has cleared. So we see the first evidence of what we might have expected. And as you might imagine, it would be very exciting to try to fill out this plot, and that's what we're actively working on. Now, another thing I'd like to mention is how naive is this picture? And I think we could probably talk all day about exceptions to this idea that somehow there's an inner disk that's reset and outer disk that's inherited. But one thing I want to mention is one transport process that we have some hope of actually studying, and that is radial drift. So the idea here, and we already heard about this from Leonardo Testi, is that grains in disks migrate inwards because of the pressure gradient in the gas. And the degree to which they drift depends on their size. So small grains kind of move with the gas. Larger grains move faster than the gas. And the largest grains kind of stay where they are. Now, the reason we have a hope of measuring this kind of transport is due to the following reason. that if you have grains freeze out beyond the snow line, they're going to be oxygen-rich and therefore O-rich. And that leaves a surrounding gas that's actually carbon-rich. So let's consider this last case here. What happens is now you have a lot of your oxygen locked up in your planetesimal here, and it does not move into the inner disk. And so your inner disk becomes relatively enriched in carbon. So you maybe have a hope of looking for high C to O ratios in the inner disk. And that, in fact, is one thing we've seen. So this shows HCN water ratios in several disks, and that's a proxy for the C to O ratio. And what we find is that there's actually a correlation between that C to O ratio and the disk mass. So one possible interpretation of this is that if you're a more massive disk, you can actually form planetesimals more easily and lock up your oxygen grains. Okay, so where are we now? So I'd like you to take away from this talk that we can now measure the volatile content of disks. We can also observe their condensation fronts, so we can start asking, where are they in the vapor phase? Where are they in the solid phase? And finally, we can start studying their transport processes. Where are we going with this? Well, I think that one of the really interesting questions we have to think about is the solar nebula typical? And I think probably the answer is no, and we know this already because exoplanets don't look like the solar system. And we're going to hear a lot more about this in the coming days. So then the question is, well, why is the solar system different? And so I think what we need to start thinking about is how the disks differ and the disk chemistry differs from source to source. We heard a little bit about some intriguing chemistry trends with stellar mass from Dmitry Semenov, but I want to bring up a couple other ones. So one is that if you look at, so we already said if you look at low mass stars, they're very molecule rich. However, if you look at high mass stars, they're very molecule poor. So that's an intriguing hint that the chemistry in these two types of disks are quite different. Then there's another result showing that the chemistry, even at around very low mass stars, can dramatically change as well. So this shows that around sun-like stars, you have a lot of HCN, and when you get to very cool stars, that HCN disappears. So again, some intriguing trends about differences between disks. So I think the question is not, is the solar nebula typical, but how do chemical variations between disks lead to planetary diversity? Now, I have a minute, so let me see if I can, yeah. So one other thing that we can do with our observations, which I think is really exciting, and I'm not sure how much is going to be covered here, is that we can, ultimately, we want to link the disk chemistry to the planets that appear in the disks. So one thing that we can do is use the volatile measurements to constrain the properties that we see. So if you see a gap opened in a disk, you may ask, well, is that due to photoevaporation or is that due to planets? And it's the observations of the gas that tell you whether it's a planetary process or not. And I think we're going to continue to see very interesting evidence for the interaction between gas and dust due to planetary growth. Okay, so thank you very much.
Thanks, Colette, and thanks for staying on time. Again, we have the microphones set up in the aisles, all three of them, as well as microphones up at the top. Let's begin with the balcony.
Hi, Pamela Klassen from Leiden Observatory. I just wanted to point out when you were talking about the CO snow line in disks, it's not that ALMA will see that, ALMA is seeing that. In the science verification data of HD 163296, the paper came out on AstroPH on Monday, showing a DCO plus ring at the CO snow line.
Yes, that's right. Yes, and other results are very, very soon to come out, so thank you, yes.
Rude?
Hi, Rude Fisser, University of Michigan. I wanted to ask about the link between the disk chemistry and planetary diversity, because both are presumably related to the stellar properties, which in turn are related to maybe going back all the way to the molecular cloud properties. Can you comment on that? To what extent are these all related to just the initial conditions that you start out with?
Well, I think that's exactly the question we're trying to figure out. So where does the chemistry ultimately come from the planets? I mean, that's exactly what we're trying to figure out. So part of the answer is that we're trying to figure out, is there inheritance or reset? And then the other thing that we can explore with the disk observations is how the chemistry varies actually from disk to disk in the later stages. But I'll leave it up to other people to decide whether the clouds are different from source to source. Yeah.
Tom?
Hi, Tom Quinn, University of Washington. So Stardust data shows that there's significant thermal processing of material that presumably came from the outer reaches of the solar system. I wonder how that fits into your reset inheritance picture.
Yeah, I mean, I think what it's showing is that you have a reset process somewhere, and then you also have a lot of transport. And I don't think that we know the answer to how the transport happens yet. And part of the answer may have to do with these transient accretion events where you really have high energy events, and then you can maybe have very high accretion rates where things move around. But we just don't know the answer yet.
Over here.
Let's see if we can get it to turn on. There we go. Wes Fraser, Herzberg Institute for Astrophysics. I really like your inheritance versus reset comparison, and I'm wondering if you've thought about the reset that might occur during planetesimal growth due to the heat from collisions and gravitational accretion, all that sort of thing. Might be appropriate for a later talk, but just curious if you've thought about that at all.
Yeah, I don't think I've thought about it much, but again, I'm an observer, so my perspective is let's see what's there, and then talk to people about the processes that can actually change the chemistry in the disk. So it's a good point.
Morby?
Morby from Nice. So you showed these diagrams from Canyon about the location of the snow line as a function of time. But I would like to point out that this line seems inconsistent with the data we have in the solar system, because as you showed, there is a lot of volatile depletion in ordinary chondrites, astatite chondrites, the Earth. And we know that these meteorites, for instance, formed about 4 million years after CRI times, and they are very volatile depleted, and they presumably formed in the asteroid belt. So somehow, some process prevented the temperature to drop so dramatically. Rebecca Martin and Livio have an interesting model on that. There may be other explanations. So it would be interesting to understand actually what prevented the temperature from dropping so low and how genetic that process is.
Yeah, so I just, thank you for saying this, because I think it points out a little bit of a disconnect between the astronomy community and the cosmochemistry community. And part of the point of our chapter, I think, is to start those conversations. So definitely come talk to us and anyone else who is thinking about snow lines and actual observations of them. Yeah.
I'm Rwanda from Hebrew University in Jerusalem. So you said that the solar system, according to your results, is atypical. So presumably the proto-solar disk. Can you elaborate on this?
Well, I'm going to really leave that to the exoplanet people later in the week. But I think if you look at exoplanets that we know about, then none of them look like the solar system. And yes, there's some observational biases. We can't see the outer planets yet. But essentially, the solar system is not a typical planetary system. So we don't know yet. So one question I've been interested in is if you could pick one protoplanetary disk and say it was like the solar system, which one would it be? We just don't know the answer to that yet.
Before Morby asks another question, I'd like to ask one connecting, you described this depletion, if you will, or underabundance of carbon in some of the solids in the inner solar system, and connect that to your C to O ratio. There's some ideas that carbon solids can be processed at high temperatures, and that can also increase the C to O ratio, maybe in a way similar to your large body growing fast and retaining the water outside. And I wonder if you guys have thought about that.
No, so we'll have to talk. Yeah, that's interesting.
Morby, you want to close this out?
Yeah, I have a second question, if I may. So concerning resetting versus inheritance, and interstellar grains, as far as we can trace them by isotopic anomalies, seem to be very rare, even in comets, according to Stardust results. So would you like to comment on that?
That's interesting. So maybe you're saying that it can't be inheriting a lot of information from the cloud. Yeah, I have not thought about that, so. Yeah.
Thomas, I think, wants to add something to this discussion.
I mean, normally organizers should not comment, but I would like to comment on that. We should remember that we only see these interstellar grains because they are isotopically anomalous. But there are a lot of isotopically normal grains which also can come from these sources which you will never trace back. So there's a selection effect.
Thanks.
And I guess just also to add, there's one thing about the inheritance that Ruud talked about, but then there's also a lot of thermal processing at relatively large radii, not just the snow line moving around, but other dynamical processes, which I think we'll hear more about as well. Let's thank Colette again.
Thanks.